Okay, we are now in page 343. In AS, we have covered atoms, nuclei, radiation. We have covered fundamental particles. In A2, we'll look at mass defect and nuclear binding energy and radioactive decay. Right? In radioactive decay, we look at exponential nature of the decay, and we define terms like activity, decay constant, define half-life. There's a relationship between half-life and decay constant. Under mass defect, we will look at nuclear fusion and fission, and we will introduce a new equation, E equals to mc squared. This mass can be converted to energy. Energy can be converted into mass. And we will look at the variation of binding energy per nucleon with A. Right? A is your mass number or nucleon number. Okay. In your past paper, you can try the homework. As I say, learning physics, you have to, after learning, you have to try out. You don't try out, it's too many formula, can't remember, and you probably don't know how to use it. Okay, that's your mind map, if you like. Just to show you radioactive nuclear energy can be, there are so many things we can study, right? But we are focusing on this part. Okay, mass defect. Right? We define and calculate binding energy by the BE or E symbol. Study the graph of binding energy per nucleon against A, and then we apply our binding energy to nuclear reaction. And we introduce Q value, right? Tell us whether the nuclear reaction is feasible. And the application to fission and fusion. Okay, divide the two parts. One part is one binding energy. Part two, we apply it to nuclear reaction. Okay, relationship between mass and energy. Right? Einstein suggested that energy and mass are related by this formula. This mass can be converted to energy. Energy can be converted into mass by the Einstein's relationship, right? Where E is in joule, M is in kilogram, T is the speed of light, 3 times 10 to the power 8 meter per second. Okay. What does this new equation or Einstein relationship tell us? Right? Today, we don't have the law of conservation of energy alone or law of conservation of mass. The two are joined together to become law of conservation of energy and mass. Total mass and energy is constant. Right? If mass disappear, it must appear as energy. Likewise, energy disappear, it must appear as mass. Okay, relationship between mass and energy. That's the relation. What does it imply? It means that when we heat a mass, we supply energy. That means the mass must increase. Heating and mass increase. Heating an insulator block increases its mass. The mass of a moving object increases Right? Where it's moving, it has speed. And then Einstein relation tells us mc squared. So the mass must increase. But we will discover that the increase in mass is too small to be detected. Too small. Atomic mass unit is based on carbon-12 scale. Carbon-12 has 6 proton and 6 neutron. Sample of pure carbon-12 are much more easier to obtain than pure hydrogen. Unit is used to measure mass of proton, mass of neutron, and electron. Usually we don't want to use like 10 to the power minus 27, the power minus 31 always, but when we use atomic mass unit, we can work with small number. And then remember, the atomic mass unit is the average mass of a proton and neutron in a nucleus of carbon-12. Right? One atomic mass unit, 1U, from the definition is 112 mass of atom carbon-12. 12 gram of carbon-12 contains 6.03 times 10 to the power 23 atoms. So mass of an atom, right? Just take 12 gram, right? Convert it to kilogram, divide by Avogadro's number, and we get the value 1.99005 times 10 to the power minus 23 kilogram. Right? Remember that carbon-12 have 12 nucleons. So average mass of a nucleon, right, we divide by 12, value, divide by 12, we get 1.66 naught times 10 to the power minus 27 kilogram. Okay, as we have stressed, atomic mass unit is the average mass of a nucleon in carbon-12. Okay, data and atomic mass unit. Right? Electron, that's the mass. You don't need to remember. If you need to use it, it will give you. But when you come to calculation, you cannot round it off. Right? They give you many decimal places you have to follow. Only probably at the end, maybe after your calculation, you want to round it off, you can round it off. But in a calculation, you cannot round it off. Okay, this one is given in the data sheet. Mass unit, as I say, is convenient. It's a unit for mass of atom, nucleus, proton, neutron. Keep on stressing, is the average mass of a proton and neutron in carbon-12. You have to keep the number of significant figures that's given, cannot round it off. If you round it off, for example, here to 3 decimal place, you will to 2 decimal place, then you'll find proton and neutron have the same mass. Okay, because the mass is, there's a slight difference between mass of proton and mass of neutron. That's the reason why we have to go to so many significant figures. What can we find in data sheet? That's not what is given. As given, elementary charge, Planck's constant, unified atomic mass, mass of electron, mass of proton. Okay, one atomic mass unit, that's the mass, the measurement of mass, is equal to 931 mega electron volt energy. That means if that mass disappears, then you produce 931 mega electron volt of energy. Okay, let's calculate it out. Use on atomic mass unit, right? Change it to kilogram, 1.6 and 10 to the power minus 27 kilogram. Then we use Einstein conversion, how much energy we can get from this mass. So that's your m. That's your m. That's your speed of light. Square that. We get 1.494 and 10 to the power minus 10 joule. Right? We want to show convert to electron volt. So we know why electron volt is 1.6 and 10 to the power minus 19 joule. Okay, so we can convert that energy divided by 1.6, and that is what we get. So we get 934 mega electron volt. There's apparently a difference between these two values. Why? Why is there a difference? Well, the reason there's a difference is because the speed of light is actually a round off figure. It's about 2.9999 something. We round off. Same with this mass set. It's a round off figure. It's approximation. So that's why this value and this value differ. It doesn't matter. Exam they will give you if they want to use this one. Electrostatic and gravitational force between nucleons. Right? Nucleons are proton and neutron. So in the nucleus, you have protons and neutrons. Protons are positively charged. So the force is the force between proton will be electrostatic repulsion, and the force is quite large. There's also force of gravity, gravitational force between proton and proton. But this one is a very weak force, as we had calculated earlier when we studied gravitational force. Right? Force between proton and proton, gravitational force between proton and proton is very small. So usually we neglect that. We can calculate out. Right? Two protons in a nucleus is about 0.15 meter apart. That means the size of the nucleus of the distance of the distance between the center of the proton and the center of proton contact. And we find that the force of gravity, gravitational force is 1.9 times 10 to the power minus 24. And we can calculate also the electrostatic force using Coulomb's law, and we find 330. So we find that that is very much larger than this one. Won't bother about this one, they're too small. Won't affect the repulsive force. Or we can take a ratio. Ratio show us clearly okay? The electrostatic force is 10 times 10 to the power 36 times greater than the gravitational force. Same with neutron. Right? Neutron and neutron will attract each other. Neutron and proton will attract each other with gravitational force. But as I say, gravity is very small. And neutron doesn't have electrostatic force. They are neutral, no charge. But we see that most nuclei or most atoms are stable. For example, helium nucleus is stable. It has 2 protons and 2 neutrons. Of course, you will reason it out. What holds them together? Proton and proton, of course, you can have 2 proton and proton exist together because they have repulsive force. But then it comes to neutron must have a contributing factor. Right? Proton and proton repel with electrostatic force. And this electrostatic force is It's a repulsive force, and we call it long range. That means act over long distance. It exists outside the nucleus, not within the nucleus alone, but the distance it covers is far outside the nucleus. That's what we study in Coulomb's law. Force is given by that formula. Since the nucleus is stable, there must be another attractive force there between the nucleons. Right? So we call this nuclear force. It must be stronger than the repulsive force between the proton. So we call this nucleon force or nuclear force. Basically, is strong attractive force. Short range, right? It just exists about within the nucleus as well. Outside is zero. So outside the nucleus or a few nucleon diameter away becomes zero. Right? It's getting weaker and weaker outside the nucleus. Right? These are all reasoning only. And this nuclear force must exist between nucleons, holding the neutrons and protons together to form a stable nucleus. And these forces are independent of the nature of nucleon. That means it doesn't matter whether it's proton, neutron, or proton and proton, or neutron and neutron. It exists between them in the nucleus. That's why it holds them together. Okay, we can see roughly as one representation. The red one is the electrostatic force. And then the blue one is the nuclear force. Okay, so you can see that this is the separation. Right? 2 times the separation or 2 times the diameter becomes very small already. 3 times it disappears completely. The last distance greater than the radius, the attractive nature of the force turns to repulsive. Only the electrostatic force applies. This ensures that the nucleons remain as a separate particle, not a continuous mass. Okay, so it exists as separate particle, not as a discontinuous mass. Okay, so these two forces, electrostatic force and nuclear force, determine whether the nucleus is stable. An unstable nucleus, we know, it decays to a more stable nucleus. Where the nuclear force is present, there must be energy required to separate the nucleon. Right? Just like you have positive charge, the nucleus, and then we have the negative charge, the electron, right, orbiting the nucleus. If you want to remove the electron, you need to give it energy to remove the electron or ionize the electron. So energy is required to separate them. Same, where the nucleons in the nucleus have a attractive force, we need to do work or supply energy to separate them. So what is binding energy? It's the minimum energy required to completely separate. Completely means you go to infinity, far away. They are independent. They are no more attractive force involved. Right? Completely separate the nucleons of a nucleus. Or we can think of it as all the proton and neutron that make up the nucleus. We call it constituent nucleons. Right? They are from infinity, they come together to form the nucleus. So the larger the binding energy, the greater its attractive nuclear force. Potential energy and binding energy. In uniform gravitational field, the potential energy is given by mgh. And we know that the potential energy is large if the height above the surface of the Earth is large, or the mass or the weight is large. Likewise, the binding energy is large if the attractive force is large also. Same as the Earth. Right? This is the weight, this is the attractive force. Right? Attractive force is large, potential energy is large. So binding energy is like potential energy. If the attractive force is large, the binding energy is large. Okay, mass of nucleus. Okay, one thing we have discovered, as you can see from the diagram, right? Mass of nucleus, this one, is found to be less than the sum of the masses of the constituent proton and neutron. That means if we add the proton and neutron that is found in nucleus separately, we find that they are heavier than the mass of the nucleus alone. Okay, just to review, your A is a mass number or nuclear number, and then the Z is your proton number, X is your chemical formula. For nuclide, the neutron number is just your A minus Z. So what we have said is that the total mass of nucleon, right, N is the number of neutron, and the mass of neutron, plus Z, number of proton, and the mass of proton, add together the total mass of all the nucleons is greater than the mass of nucleus. Right? As you can compare, right? You can compare for helium nucleus. Right? Helium is made up of 2 neutron and 2 proton. We add the mass up, that's what we get. Remember, we know the mass. We know the mass. Mass of proton, mass of neutron, we know. Right? And we compare the mass of helium and the total mass of all these nucleon. There's a mass difference. There's a difference in mass. We call it mass difference or defect. Why? Why there's a defect? We will be answering that in a while. Right? There's a mass difference, a defect. So we call it a mass defect. A difference between the two mass. The mass defect or mass excess is just a difference in mass between the total mass of nucleon in the nucleus and the nucleus. That means we take the total mass of nucleon minus the mass of the nucleus. That's your delta M. Right? Total mass of nucleon, mass of nucleus. Right? There's a difference in mass. Then we can use that to calculate our binding energy. E equals mc squared using Einstein's relationship, where m is in kilogram, c is the speed of light, and this difference in energy or this difference in mass, right, is released as energy when the nucleons come together to form a nucleus. Okay, just to remind you the conversion between mass and energy. Right, so we can calculate the binding energy per nucleon. After we calculate the binding energy for the nucleus, then we can calculate the binding energy per nucleon. Right? It's just the total energy needed to completely separate all the nucleons in the nucleus divided by the number of nucleons. It means the binding energy of the nucleus divided by A, the mass number. Right? Then we can compare one nucleus and another nucleus. It's unfair to compare, a nucleus has 10 nucleons, and a nucleus have 2 nucleons. There's no comparison. But if we take the binding energy per nucleon, then we can compare. Right? How strong is the nuclear force? Okay, let's do an example to calculate the binding energy for helium. Usually they will give you. Right? You have to go to data sheet, whatever is not given you. Mass of helium nucleus is that given you. You are asked to calculate the mass defect of helium, binding energy, and binding energy per nucleon. Okay, so as I've said, this is always given. Not in data sheet, but they will give you if they require to calculate. Okay, so usually there has 2 proton, 2 neutron. Each of them has atomic mass unit. We add them up, that's what we get the total mass. And then there's the mass of the nucleus. So mass defect, we just subtract total mass of the nucleons minus the mass of the nucleus. That's what we get. And binding energy, we use Einstein's equation, E equals mc squared. If this is in kilogram, but if it's atomic mass unit, we just use a conversion factor 931. Then we get 28.4 mega electron volt. Right? As 1 atomic mass unit is 931 mega electron volt. Right? That's the mass. Convert to energy. So we use this unit. Then we want to calculate, finally, binding energy per nucleon. We divide by 4. And we get 7.1. This is very high. Right? We'll show later on, most of them is about 8. So for helium, this is quite high. So helium is very stable. Okay, let's compare atomic energy and nuclear binding energy. That means ionization energy. I can see ionization energy for hydrogen. It's about 13.6. Whereas when you break up the alpha particle, that's the energy, very large. It's about 2 million times greater than ionization energy. So you can see that a lot of energy is available in the nucleus for us to use. Right? Nuclear reaction, let's compare nuclear reaction and chemical reaction. Nuclear reaction, the driving force is the loss of mass. Right? Chemical reaction, bond breaking, bond making, new bond form. Nuclear reaction, mass and energy is conserved. Chemical reaction, conservation of mass. Nuclear reaction, the energy is 10 mega electron volt. It's always in mega electron volt. Ionization energy is about 10. About there, just a comparison, approximate value. And nuclear reaction always will produce gamma ray photon. Whereas chemical reaction, it produces ultraviolet photon. Okay, stability. Similarly, we can calculate the binding energy per nucleon for every nucleus and then plot a graph of binding energy per nucleon against the nucleon number. Right? Remember, the smaller the binding energy per nucleon, the easier it is to separate the nucleus from its other nucleons. So a stable nucleus is one which has a very low probability of decay. Right? We will study radioactivity after this topic. Less stable nuclei are more likely to disintegrate. Right? If it's stable, the nuclear force is very strong inside the nucleus. Less stable, nuclear force is a bit weaker lah. So a useful measure of stability is the binding energy per nucleon. Right? Normally in exam, they will give you a basic shape only lah. Right? They will minor detail around here, they will eliminate lah. So you don't need to worry so much about that. Right? That is a normal shape. Okay. And the last one there is uranium-238, 92. At the end there. Okay, let's see some of the features. 347, note. You can see that it rises and increases as your A increases to about, you can see around about 15 there. 15 there is around about 8 already. Nearly 8. Come to 8. So most, these are all the lighter one. Right? So we can see that most of them are around 8 mega electron volt. Right? The lighter one is less than 8. Right? In general, the mass number greater than 15, right? All the nuclei have a binding energy about 8. Right? And then we can see the highest one, 60. A60 is iron. Right? The most stable, yes, 8.8. Right? A60, iron, binding energy per nucleus 8.8. So this is the most stable. Right? Remember, we say the greater the binding energy per nucleon, right? This is a greater force. So we have to do more work to remove, to separate them, to different, to form individual nucleon. Right? After iron, yeah, it starts to decrease. Right? It's still all about 8. As I say, iron more stable. Less binding energy, it means that we need less energy to put into the nucleus to separate them. That's what need to be done. And then we can see this helium has a large binding energy that we have calculated earlier. And for heavy nucleus here, right, when fission occurs, the nucleus break out into 2 lighter ones. And the binding energy, right, if it's here, it move up to there. Right, 2 lighter one will be somewhere around here. So we can see that the binding energy increases. Right? That's why this one we call it fission. So it means that if we have a nucleus here and you break up the 2 smaller one around here, binding energy increase. So it means that this reaction will give out energy. Energy will be released. Right? Depending on where it is. Right? That is the energy release. Fusion. Fusion on the other hand, we take lighter nuclei from here. Lighter one. We form a heavier one here. Right? Now we see also energy is released. Right? Whereas if we take nuclei around here and form Right? From bigger one also, around here, very little energy is released. Very little. Right? We will show later on for nitrogen and to form oxygen. It's not worth it. Right? That nuclear reaction. We are more interested in fission, which we use for nuclear reactor, and fusion, which is provide hope for the future energy supply. Okay, and nuclear reaction is very little only here, around here. Right? And gold. Why gold? Because you want to be rich, you have more gold, right? And we see that to form gold, right? What all this tell us is that to form gold, you need to supply more energy to make gold. So it's not worth it. Right? Gold is not easy to produce. So much energy that is not worth it. Right? Geiger Mason scattering experiment. Right? We send alpha particle from radioactive decay towards the nucleus. It's the first step to learn about atomic structure. Right? Of course, we don't want to stop there. We are interested in the nucleus. Right? The next step, what happens if we send alpha particle into the nucleus of the atom? Right? So remember that alpha is positively charged, nucleus is positive charged. There is going to be repulsive force between the two. So that's the reason why we need to accelerate the alpha particle to give it higher kinetic energy before it can enter the nucleus. Once it enters, the attractive force will take over. The nuclear force will take over the attractive force. But as far as outside the nucleus, the repulsive force is strong. So you have to overcome that. Okay, nuclear reaction, artificial radioactivity. First nuclear reaction was performed experimentally in 1919 by Rutherford, who exposed nitrogen to alpha particle. Right? Where did he get it? From radioactive element, radium. At that time, they have no idea how to accelerate the alpha particle. So they have to use alpha particle from a radioactive source, radium. And the product is oxygen and hydrogen. Right? We will show later on the nuclear reaction using binding energy that this reaction is not worth it because you have to accelerate the alpha particle. You have to provide energy. Not worth it. Right? That's your alpha. You send it to nitrogen. You produce oxygen and proton. And then we can write the equation. That you should be able to do. That's your A as well. Okay, so this one show you that there's a few things we can learn. Binding energy for helium and carbon and oxygen are especially high. And as I say, around here, no point in the nuclear reaction doesn't generate energy. It's only for experimental purposes that we're interested in. Only where fusion, this one, is to form helium, you can see release of energy, or far away there, uranium, right? Where it break up into something around here, then you will have release of energy. This one is very small. Okay, energy is released, that's very small, not worth it. Right? We have to compare the amount of energy we put in and the amount of energy released. If you're going to spend more money to to produce energy, what's the point? Okay, I think we have said that already earlier. Right? The alpha and the nucleus are both positively charged with each other. Right? So it's difficult to bring the two positive charge together. Right? As it comes closer and closer, the repulsive force becomes greater and greater. But that's why we have to accelerate the positive charge. But the discovery of neutron in 1932 helped overcome the problem. Why? Because neutron neutral, no charge. It's not repelled. So as long as we can send it to the nucleus, it will enter the nucleus. Right? Attractive force take over. Attractive nuclear force will take over. Right? Being charged and heavy, right? Not electron. Electron is too light. Heavy in atomic scale. Neutron has a high energy even when moving slowly. And it's good to initiate nuclear reaction. So by 1939, many nuclear reactions have been studied, but none seem feasible as energy source. Remember, people don't want to produce energy. When to produce energy, then it can benefit us. We can use to generate electricity. As I've said, energy is released, nuclear reaction, but we have to spend more energy. Right? As I've said previously, nuclear reaction here, around here, for all this one, of no use. Right? Energy is released through energy released in the reaction, but more energy has to be expended for the reaction to take place. Right? And only a small fraction of the reagent particle will react as desired. Right? Only, remember, they are all very small. So there's no guarantee that when we send the alpha on there, all will interact. Not all. Some will miss out. Right? Very few will interact with them and produce the product that we want. And there is also very little chance of a second collision. Right? So it's not worth it. It's like wasting money. If you can get your product near your house at $10, and there's one selling at KL $8, and you have to drive there to get there or take a bus there. It's not worth it. Right? Bus fare may cost you $4 to and fro. So what's the point? Not worth it. Doesn't benefit us. Doesn't save any money. Question: in nuclear reactions, take the quantities that are conserved. Okay, linear momentum, charge is conserved, energy and mass. Right? It means mass can convert to energy, energy can convert to mass. Total mass and energy must be the same. Mass number, right? Number of nucleons there in a initially and finally must be the same. It cannot disappear. Nuclear reaction, special nuclear reaction can be written down in, we can write it as like chemical reaction. Chemical reaction, we can write equation. Nuclear reaction, we also can write equation, which you have learned in your AS. Okay, let's look at simple one. A plus A equals to B plus B. Right? This one we call reactants, just like your chemistry. What you start with and what you produce, the end is called the product. A capital is usually used for target. Right? Like we have nitrogen, we send alpha, that's the incident particle. The final nuclide, the product, the final nuclide, oxygen, and then emitted will be proton. Right? So when we send alpha to nitrogen, we produce oxygen, and then proton is emitted. Nuclear reaction is a process where the structure of the nucleus is changed by interaction with other nuclei or nucleons. Right? As long as the nucleus is changed, whether you say a neutron inside, or say a proton inside, then there's called nuclear reaction already. Because we'll see the product different from what you have initially. Example, nuclear fission, you have a neutron, we send it to the uranium, and it enters there, it breaks into two smaller ones, and neutron is released. These two products are different from the original. They are different elements completely. Right? Or we can have fusion. We have tritium, deuterium. Right? We force them to interact, fusion, right? Accelerate them together. Resultant is helium and neutron. These are your product plus energy. Because here will also have energy release. Okay, let's just use some symbol. MA, mass of incident particle A, mass of the nucleus A, mass of nucleus B, right? MB, mass of emitter particle. Q is the energy. Q value is a measured energy released or absorbed in a reaction. So how do we define it? We define it as total mass of reactant minus the total mass of product. Right? This is a difference in mass. The total mass of reactant minus total mass of product is a difference in mass times a C squared. Right? Convert the difference in mass to energy. Okay? In terms of mathematical symbol, that's how we write it out. Right? If we work with mass, that's how we take the total mass of reactant minus total mass of product. But if we use binding energy, right, then we have to take the other way around. We have to take the binding energy of product minus binding energy of reactants. I think just memorize it. No point in okay. So total Q value, total mass of reactant minus total mass of product. That's it like chemistry. If energy is released, we call it exothermic. The total mass of reactant is greater than total mass of product. Energy release. But if the reaction requires energy, we call it endothermic. We absorb energy, so Q will be negative. Right? In this case, the total mass of product is greater than total mass of reactant. Okay, as I said, you can show, you can derive. Right? We are patient, but usually you lose completely. It's not an easy calculation to do, but you can show that if we work with mass, this is the binding and this is the total mass of reactant, is the total mass of product and C squared, or binding energy of product minus binding energy of reactant. Okay, as I say, I won't bother to show it, it will get confusing. Right? For info, if you want, you can sit down and understand that. You can also show for this one also the same thing, right? Which I won't show, as I say, it get a bit confusing. I can follow my slide. Okay, I think we have completed for first part. Okay, we probably take a short break. operate before the second part.